Hey astronomy students, this is Mr. Ruark. We're going to finish up chapter 9 here with masses of stars. Alright, so in order to figure out masses of stars, how do we know that? Well, we need to compare them, right? And what do we have them to compare by but our sun? Well, we have to ask ourselves, are they the same mass as the sun? Are they more? Are they less? And, you know, it's kind of hard to tell just from a star. So what they typically do is they use binary star systems in order to determine masses, and they use those for bases of comparison. So binary star system, in our solar system, not in our solar system, in our universe, excuse me, over 50% of all the stars in the Milky Way are going to be in a binary star system, which means there are two or more stars that are rotating around each other. Okay, and then we know that by understanding their orbital motion and by measuring their orbital motion, we can estimate their mass. Now notice it says estimate because we can't ever be 100% sure. Plus they're constantly changing, right? Because they're gases. Heating up, solar winds are going, etc. Okay. So a binary star system, the way that works is that you have two stars that are orbiting around each other, and they're orbiting around a center of mass. Okay, around a point. It's a balance point of the system. Okay, if both of the masses are going to be equal, then the center of mass is going to be right in the middle. Pretty easy to understand, right? So we had two people sitting on this teeter-totter seesaw, whatever you call it. They're both equal. They're going to sit equal distance away from each other, so that there's no favoring towards one person or the other. Okay, well, what if there's more unequal of the masses? If one of them's more massive than the other, then the center of mass will shift towards the more massive star. Okay, so here, if we had these two here, you would have, if this big, huge ball here was sitting on the edge, then the teeter-totter would be slanted, and it wouldn't be able to go back up. Okay, so to make it more even, the center of mass had to shift towards the big star. They couldn't be equal distance apart. Okay, so estimating stellar masses, we use an equation similar to Kepler's third law. If you remember Kepler's third law, it was the period, the orbital period squared, and that distance and that time was in years, and that was equal to the cube of the distance, which was in astronomical units. Okay, so for our solar system, we were able to use that equation. And the reason for that is because this is actually the equation here on the bottom that you would use. But in our solar system, with one star in the mass of the system, we didn't have to worry about MA and MB. We just had the 1. So 1 was equal to a cubed over p squared, right? Right here, where it says MA plus MB would always be 1, because in our solar system we just have that one star. We don't have a binary star system. But in other ones with binary star systems, we have masses MA and mass MB, and they're different. They won't equal up to 1. It won't be 1. It could be more, it could be less, right? So this is how you would estimate a stellar mass. Okay, so just to give you an example of how this would happen, let's say that we have a binary star system that has an orbital period of 32 years, and the distance between those two stars would be 16 astronomical units. And so what's the solar mass of this system? So what you're looking for is MA plus MB. You don't really want to know what's the mass of A and the mass of B, unless they ask that later. Right? So MA plus MB would be equal to 16 cubed over 32 squared. Okay, now remember 16 cubed, that's A in astronomical units. The astronomical units is 16, so we're going to cube that. And then 32 would be going for P, which would be the time or the orbital period. And you would take the, you would divide those, and you end up with 4 solar masses. So the mass of that system would be 4 solar masses. Okay, and then you could use other things to help you get to estimating the mass of the individual stars in it. Okay, all right. There are 3 types of binary star systems. Okay, 3 types, and you need to know the 3. So, the first one is a visual binary system. Okay, visual binary system is when you have 2 stars that are visible through a telescope. Okay, it's only possible if they have large orbits with long orbital periods, and an example of this would be Sirius. Okay, Sirius is actually a 2-star system. You have Sirius A, which is a bright star, and Sirius B, which is a white dwarf. Okay, Polaris is actually a 4-star binary system, which means that there's 2 sets of binaries that are so close to each other that it's a 4-star. And Alpha Centauri, which is the brightest one in the sky, is a 3-star system. Okay, so this is when both of the stars can be seen directly, and you can actually see that they're separated. Okay, then you have your spectroscopic binary system. This is what happens when the 2 stars are so close you can't see them through a telescope. It looks like one big, huge, or 1 star. Okay, the only way you can see them is by looking at their spectrum, by their Doppler shift, and I guess I could actually put this up here. All right, so usually binary separation can't be measured because the stars are too close, right? And so this would be called spectroscopic binaries. Okay, so what happens? You can detect them through Doppler shifts. Okay, so the star that's coming closest to you would blue shift, okay, because it's coming closer to you, which means that the wavelengths are going to be shorter. The star that's going away would end up having red shifted lines, and then it would alternate because there's always going to be one coming towards you and one going away from you. And you would be able to tell the difference by the red shift and the blue shift. Okay, and then you can estimate the masses of the 2. This just kind of shows you an example of what it would look like, a typical sequence of spectra from a binary system. Okay, so here are your 2 binary stars rotating around each other, and it just shows that, for one would be shifted this way and the other one would be shifted that way. Okay, so just know that they're found by Doppler shifts. Then the last one, and just so that you would know, fun fact, more than half of all the stars in binary systems are, most of them are spectroscopic binaries, so they're so close together you can't tell the difference between them unless you look at their spectrum. All right, and then the 3rd type is the eclipsing binary system. This would be if usually in a star system, a binary star system, the inclination angle is unknown. So, of course, that's going to give us more uncertainty in the mass estimates, right? But in an eclipsing binary system, we can tell it's an eclipsing binary system because we see it edge on, which means they're going to cross right in front of each other if we're looking at it from Earth. And when that happens, part of the light is going to be blocked, and the total brightness is going to decrease. Okay, so here we go. And we know that we're looking at it edge on because, like I said, part of the light is blocked and the total brightness will decrease. Okay, so if the stars lie in a single plane, they can cross in front of each other, and we're seen to eclipse each other from Earth. And what we would get from this is called here we go. What we would see is here we've got 2 rotating around each other. Well, the intensity is great when they're kind of near each other, and then when one goes in front of the other, it dips. Okay, well, this is when this would be when the smaller one is in front, and then here they dip again when the bigger one is in front. Okay. Actually, no, it's the other way around. This would be the bigger one in front. This would be the smaller one in front. But they'll know because there is that dip in what we call the light curve. And the light curve is when you have intensity versus time and you graph it. Okay. This just gives you more information about the eclipsing. So there's no eclipse happening here because, well, there's Really nothing happening here. They're both side by side, right? But when the cooler star is in front and it's shining, you've got this really big dip here, which means that the intensity's gone down. And then here's when the cooler star's in front, there's not much of a difference. Or cooler star's in back, excuse me. Yeah, we don't need to talk about this. This just goes more into yada, yada, yada. Okay, masses of the stars. In this HR diagram, if you'll notice that the masses, low masses would be near the dwarfs, and the high masses would actually go up in the main sequence stars. Once you get into the supergiants and the giants, the masses actually go down, right? Okay, the higher star's mass, the brighter it's going to be, and these high mass stars have much shorter lives than the low mass stars. And this is just showing out the sun will live to be about 10 billion years old. Something that's 10 times the sun will live to be about 30 million years, and something that's about a tenth the size of the sun will live to be about 3 trillion years old. So, all right, so they'll usually take a survey of the stars, and when they take this survey of the stars, they're just kind of doing it to see what they've got out there, honestly, just to see what kind of stars we have. So it's kind of like doing a census of the stars. All right. So what did they find when they do these census of the stars? Well, they find out that the fainter stars are going to be harder to observe. So we typically have a little bit more bias towards the more luminous stars, the giants, the dwarfs, all those that are big and bright, right? And we also found that the faint red dwarf stars are the most common stars. They found that the bright hot blue main sequence stars with high masses are very rare, and they found that the giants and the supergiants are extremely rare. And I just thought that was funny, so I thought I'd put it in there, and I'll see you in class.